Hello, I'm Michael O'Connell, and in tonight's video, we're going to revisit code that we've already been writing in Colaboratory. And that code was what we used for Cardano's formula and finding the roots of the cubic polynomial for the compressibility factor that we derived. And we also made code to plot isothermic curves of pressure versus specific volume in here as well. And what we're going to do in this video actually is superimpose the two-phase envelope to model the specific volume in two phases, as you can imagine, as we change the pressure. And James Clerk Maxwell made a extremely important discovery with this when he proposed that this vapor pressure that we have has to be such that the area below and above the horizontal line, this vapor pressure that we choose, has to be equal. And that's very important for us because what that means is that these intersection points, 1, 2, and 3, are our specific volume values at that vapor pressure. So that's obviously extremely important for us to realize before we dive into this. And before we start writing code, I would like to show you this graph here on the right, which has the two-phase envelope that we want to superimpose. And I would just like to make a couple comments about this. So we call it two-phase because there is a liquid phase and vapor phase present in some sort of vessel. And we see that it all becomes one specific volume at the critical point. And again, this just harkens back to everything I've been saying in these past couple videos because, as you know, with the cubic polynomial for the compressibility factor and using Cardano's formula to find those roots, there was the case in which there is one real root, and that case is when you are at or above the critical point, in which case there's only going to be one specific volume because the properties of the liquid and the vapor become indistinguishable and they become identical. So that is just important to remember. But again, the point of this Maxwell construction is when we're below the critical point because we have some line of vapor pressure, and this is important because we need to know, well, what pressure do we need to have so that we have the correct specific volume of our liquid and the correct specific volume of material that will be in our vapor phase. And in this case, we're going to stick with what we've been using, which is water. And I think with that, I think we're ready to start adding some code in here. So for this function that we're going to write, we need two different things. We're going to need some sort of integrand, and then we need our bounds for integration. And we're actually going to use something really cool from SciPy to integrate and find areas. And what we can do here is just supply our function, and that's going to be the integrand that we need, and then put in our bounds, and it will return the integration of a polynomial. So this is sort of the first step with this Maxwell construction, is we need to have something that actually calculates the areas. Then we can probably use a root solver to adjust this pressure line, right, until we get equal areas, in which case we can accurately superimpose our two-phase envelope on our plot up here. So let's get started with that. So this first function I'm going to call bounds because it's going to be our bounds of integration. That's one of the things we're going to need. And to get these bounds are actually, it's pretty simple. These are going to be our three volumes, which are obviously going to depend on pressure that we supply and temperature. So we can call these volumes in another line V1, V2, and V3. And we can use one of our functions that we already have Cubic pressure, that's not it. Cubic volume. Sorry about that. That was sort of embarrassing that I had to scroll all the way up to find that. But even though it was literally right above me. But that's what we would use, right? So these volumes, once again, those are going to be the bounds of integration. And looking back at the Maxwell construction, that's V1, V2, V3. Boom, boom, boom. Okay. Next thing we're going to need is we need our integrand. And what is that going to look like? So let's write a new function inside of this. So integrand. And what are we integrating with respect to? Well, that's going to be whatever's here, right? X-axis. So that's specific volume. Okay. Good. And then what we have to think about here next is like, what actually is our area? Well, the area you would be computing with an integrand is this pressure here, this line, right, this function, minus this function. Because that's how we always find areas. If you remember maybe from a calculus class, you subtract two different integrals. So that is exactly what we would want to do here. So let's see what we would have. So one of these would just be P, that's that pressure that we supplied. And what this would be, again, this is our guess. This is picture us like taking, a little ruler, maybe something straight along this graph, this isothermic curve, and we're moving that pressure along, and we want to eventually, the goal of all this coding is to find that pressure that we hold there such that the area below and the area above are equal. So let's figure out what the other curve would be. And fortunately, this becomes a lot easier because this is what I was thinking of, is cubic pressure. So from there, we are going to be able to compute. Oh, I just lost it again. Oh, scroll up too far. From there, we're going to be able to compute what the pressure is, and that's going to be this, right below. So let's see what that looks like. And this, sorry, I should have specified, obviously, this is going to be the return for this function. Very, very simple, right? This is our integrand, that's what we want to return. And then the next thing we're going to need is the return for this. Before we write the return, I would like to play around with quad, just so we get kind of a sense of how this works. So let's just define some function, f of x, and then we will return x cubed. If we want to use quad for that, like I said, we're going to supply our function f. And if I didn't already show you, I did put that in our code up here, and I made sure to hit runtime all. But we have scipy.integrate import quad, so we are getting that from the scipy Python library. Okay, so this is our function, right? And then our lower bound, we'll just do 0, and upper bound 1. Okay, and if maybe you can try to find the integral of that function quickly in your head and figure out what this would be. But let's see what it is. And if you guessed 1/4, you're correct. But notice we have this other value too. And this is your error approximation. That's something that you do a lot in calculus too. And that's just, we don't need that. We don't need these two values. And since this isn't a tuple, we can just index that for 0 so that we get only the first value. Okay, so hopefully that just shows you a very quick, easy, simple way to use quad to do integrals. Okay, so let's use it for this one. So what's our function? Our function is integrand. I feel like I'm spelling that wrong, but if I am, then too bad, right? And then I think we're going to start from there to there, so let me make sure. Okay, I didn't capitalize anything. Just want to make sure of that. And then we want 2 areas, so I am going to separate that with a comma. Okay, so those are going to represent our 2 areas. What we need to do now is use the root solver, and to do that we need to define a function that we can supply to the root solver. And specifically, we want to find a certain pressure value that makes these 2 highlighted green areas of our Maxwell construction equal. Specifically, we want the sum of this left area and the right area equal to 0. So let's see if we can do that. So I'll define this function as the sum of our areas. And notice that with the SciPy root function, the function that we supply needs to be a vector function, okay? And that, don't worry, that will not be too much of a problem for us. We'll just put an arbitrary vector in there for the function, and then we can supply arguments that we're going to need. In this case, we actually do need an argument, because remember, we already wrote this function. Actually, this is bounds, but these are our areas. This is left, this is right, okay? So we need those in here because that's what we're going to try to make the sum of these 2 equal to 0, okay? So we do need the temperature because we have that here. And that is what we're going to use in here. So we're going to use bounds with the pressure and temperature. And we need to unpack this into our 2 areas. And like I said, they're left and right. This is good. The only thing we need to put here is that we have a vector here, but we only have 1 pressure. I mean, look, it's just this line. It's 1 pressure. And that's not a problem. We can just set P, this pressure that's here, equal to the first value of this vector, right? So just vector index 0, right? Not a problem. That way we only have 1 value. So it's not going to mess anything up when we use the root solver. Then what is our return going to be? Well, it's simply the sum of the left and right areas because that's what we're trying to set equal to 0. So that should work perfectly for us. Before moving on, let's put our function to the test by using the root solver. And we'll use it with something we know. So our function is going to be sum areas function, right? Then we have our vector. So we could just put some guess of pressure in there. We'll do atmospheric pressure in pascals. And then args is just our temperature. So we know that the boiling point, or the normal boiling point, is going to be 373.15 Kelvin. Okay, so let's see what this gives us. I'm very curious. Okay, there we go. And we have this value down here. That is your pressure. Okay, and obviously you might be thinking, okay, like, why isn't it actually 1 atmosphere? And the reason for that is you have to realize that this whole thing that we have in this notebook, all this comes from is the critical point, right? We have this critical temperature here, the critical pressure. Everything else we derived. So that's pretty impressive. Given just the critical point, we've been able to plot isothermic curves of pressure versus specific volume. We've been able to find specific volume values and all of that with the pressure and temperature supplied there in that cubic volume function. And now what we're trying to do is see if, or actually what I tried to do here is see if the pressure corresponds to what the pressure actually would be at the normal boiling point for water. And okay, it's not perfect, but it's pretty close. So that is pretty impressive for us. But when we're going to use this root function, all we want is this value, and it's stored in a 1x1 array, and it's stored under X. And we know that we use .x, so we know that, right? Okay, now it's in an array, and the way to get that out is we index it, right? And it's only one value, so the index 0. So that's what we're going to be using. Now that our root solver is working properly, we're ready to actually start trying to superimpose our two-phase envelope on our plot up here, okay? And to do that, we actually have something that can compute our pressures now, which is awesome, and that's thanks to this root solver. So I'm actually going to store this under a variable, and because pressure is on the y-axis, I'm just going to call it y. And we also know that when we are making the two-phase envelope, I want to show you something here. We see that there's different temperature curves here. So temperature is also going to have to change, and that was one of the arguments here. So I'm actually just going to call this temp, okay? Which, if you are really smart and you can guess, that actually stands for temperature. So we'll set that equal to 373.15 because that's what it was before. Okay, so now we have our correct pressure stored from our Maxwell construction. And what that means is we can actually get these volumes. So let's use our cubic volume function that we have from a past video to get that, okay? So what is that going to be? Well, that's going to return 3 values in this case, 3 volume values. And that is because we are below the critical point. And I'm doing VL, VI, and VG just for the volume of liquid, intermediate volume, which is just nothing, and a gas. And actually, since it is a nothing, we'll just put it as an underscore. That way, if someone was reading my code, they wouldn't be like, oh, what's this other weird volume? It's like, no. It's artificial. It's just from the cubic polynomial, the cubic equation of state that we use to model this sort of thing. That's all that's a part of. Not a minus sign, we want underscore. Okay. And we can actually print these out, which is cool. So let's see what our volumes are. Or actually, these are specific volumes. So these would be in cubic meters per mole. And we have to close that, don't we? Yep. Perfect. Obviously, we're at the normal boiling point, so there is a lot more. Not a lot, but definitely more gas than liquid, which is something that I think we would definitely expect. So that's cool. That's definitely working properly, which is excellent. Okay, so what we want to do here is we want to plot our two-phase envelope, and to do that, we need lists of values, right? We need data to plot, and we can store those in lists, and that is exactly what we're going to do here. And again, our y-axis is pressure values, and then V, that's the specific volume. So that's what we're going to want lists for. The key thing to remember here is we're not just going to have 2 lists. It's not just going to be like, oh, X and Y. We are going to have 3, because when we're below that critical point, we also have VG. We have the volume of material in the gas phase, right? So let's start by making a list for the pressures. So we'll keep our variable Y consistent there, and just a list. And as you can imagine, what we're going to do is we're going to be able to append values for this. And as I said before, when I showed you the two-phase envelope, we have different temperatures. And as we did in a previous video, we're going to change these temperatures using a for loop. So we'll do for temp in some sort of range, right? Lens space. Okay, we'll start small, so like 250, sure, that's fine. To 475 by steps of 25 temperature, that would work. We want these we definitely want under our for loop. And the lists, these are empty lists, so we can start them outside, but we want one for our specific volume of liquid and our specific volume for gas. Okay? And what we can do is, let's put this down here, dot append. And so each time we iterate through, we're just going to add another Y, right? We're going to add another pressure. to plot. And that's what's going to make our list real there, okay? So for VL, oh, whoops, I want this to be list. That way we know what we're doing. Because these are something else. These are those values. That would not be good for us, would it? So let's try that. List dot append, and then we would add our extra liquid volume value, and then we're going to do the same thing for the gas here. Okay, there's something else that I notice here, and that's our guess here. Okay, so we have to supply a guess when we're using the root solver. So let's just start at something. We want to start somewhere, right? And this is going to change too, because we don't want to always just have some arbitrary pressure as our guess every time we're going to go through the loop, because at some point it might be like so far inaccurate that it diverges and you don't even get a pressure and your whole thing fails and you're not going to get any phase 2 envelope. That's not what we want. So because we're starting at a small temperature below the freezing point of water there at 250 Kelvin, let's just start something small. Doesn't have to be crazy like Pascal wise. Like let's start just at 1,000 pascals. And then here we can put in our guess there. Okay? And then what we can do is actually after that we can have our guess set equal to our new vapor pressure value. That would be absolutely perfect, wouldn't it? Because then it's not going to be a perfect guess every time, but it's what your previous vapor pressure was. So I think that's going to work very well for us. Now let's check to see if everything works. So shift enter on this, and we have a problem with the for loop. Lens space is not defined, and that's because I didn't use numerical Python that we have imported above. So I do need to change that. Let's change these a little bit. Let's do smaller steps. Go to 500 to 250. Let's put periods on the end of these so that they are floating decimals and not integers. That should be good. Uh-oh. Oh, no. That's a huge, huge mistake. Okay, this pressure is going to be our Y, right, that we computed using the root solver. This temperature is going to be temp. And because nothing is going to affect us from what's above here, I am just going to change this back to T. I'm quite indecisive that way, but I like to keep things as simple as possible when I can. So that should be very good for us. Okay, awesome. It actually works. And let's check our list of specific volumes for the liquid water. And we see change. And change is important because that means it's working. Because the way it was before, if we had just had this as those values when we used this cubic volume function when we tested it in that previous video, then all of these would be the same. So that would not be good. Okay, let's do a little copy and paste action so that we can make a new plot. That's exactly what we're going to do. And I'm just going to change these to plot. Okay. And obviously we're going to want everything that we had before. And let's set a range for our x-axis, actually, since we're at it. Let's make this the minimum volume, and yeah, we'll go to like something small like that. But we are on a log axis, so we will need to take the log base 10 of whatever we want to actually be our minimum and maximum. So let's do NP log 10, and then the minimum of our volume V. And then we'll just do -3 for that. Similar to what we have here up here in the log space. Okay, but all of that can stay. That's not going to be a problem for us. And then we want to add more scatter, right? We are gonna add, and we don't want this in this for loop because that will go, that's just for these, to plot our isothermic curves of pressure versus the specific volume values from before. And then this time our x is going to be our list of volume values. And let's actually do a name for this. So we'll do liquid phase. And then we'll actually do line color. And I'm doing this because we are going to do the same thing, actually. Let's make this black. We're going to do the same thing for the gas volume in our vapor phase. So plot.add scatter, right? So VG list, right, is, oh, and then I forgot our Y. That's going to be our Y list now, because those are the pressures that we find for our Maxwell construction using the root solver. So that's fantastic there. We do want our mode to be lines because we want this to be a nice smooth line there. And we'll call this vapor phase. How about that? And let's see what we get. Some sort of problem here with this. Oh, parentheses. Yep, gotta get that right. I struggle with that. Something is wrong again. Okay, because this is off, I'm not going to worry about it right this second. Okay. But as we can see, our range is too far, so I do want to adjust this. So let's see if I can write it correctly this time. So 10. And we do want our minimum volume. None of that should have been a problem. And then how far do we want to go over? Well, let's see, this would be 10. We don't want to go far. I would say that's not good either. That's to 100. Let's see where this intersects here. Okay. Let's do -2 should be good then. So just to show you on the graph there, that's right here. Okay. And again, this is because we are on the logarithmic scale for that axis. Okay. So the next thing we have to do here is we have to get these two to meet, right, for our envelope. What we have so far here is pretty good, but as you can see here, we need to connect these two, right? That's definitely a tall order. And what we need to do is just have them connected by adding lists together. And that makes obvious sense for our volumes because we have one specific volume axis, so we can just have one list. We'll call it our V plot because this will be for plotting purposes. And we need to add our list of, whoops, oh no, our list of specific volume values in the liquid phase, right? And what we have in the vapor phase. The problem here is that, as we can see, for the liquid, as we're moving across the specific volume axis, we're increasing. But as the vapor specific volumes come to meet at that point, we can see here that we're decreasing these specific volume values. So we need to reverse the order of those values so that we meet properly. And we can do that with that, right? The same will need to be done for pressure, and we'll call this P plot. And this is going to be our Y list. Now again, we are going to actually have to do the same thing because as we move up this curve, the pressure is increasing, and then we move back down the curve and the pressure is decreasing. So it's all about how we're approaching this point. That's what's going to dictate the order here. And that's why we use this, which again, this type of syntax you can find on, I should have something here with W3 schools with the lists. And oh man, there is just tons and tons of good things. Maybe sort lists, it might have something like that. Notice that we sorted our specific volume values in the last video, but it might actually be something here in with indexing. That would not surprise me at all. But you will find it in here at some point. So that is what is obviously super, super useful for us here. So let's see where that takes us. Okay. Make sure that's correct, and it seems to be. Now what we want is we want V plot in here, right? And P plot in there. And then now I'm just going to change this name to two-phase envelope. And yeah, since we have the white background, all this stuff should be visible. All right, awesome. So this is much, much better. There's only one problem that I can kind of see, which is that we've seemed to connected them properly, which is excellent. That's exactly what we wanted to see there. But this is like a straight line. So that is not what I want to see. We want it to look like this. We want it to be a smooth curve. So let's see how we can do that. The problem that we have here that's causing this straight line that we see is mainly due to the fact that we are assuming that the change in temperature is linear. And that obviously is just not going to be true. As we increase from our liquid-specific volumes and decrease from our vapor-specific volumes approaching the critical point, our changes in temperature are going to get smaller, which means that this constant step that we have supplied for our for loop 10 for changes in temperature is not going to be right, because we're going to need this to decrease as we move forward. So at first on our isothermic curves, again, we're going to be taking big steps, big changes in temperature, and then smaller ones. So this shouldn't be too bad of a fix. All we need to do is have temperature depend on a different variable that we can adjust, and then that way we can control the way in which temperature changes. In other words, I'm going to use Desmos to make some sort of function that we can use to model the changes in temperature. So temperature would be our dependent variable, and I have this in here. So it'd be y equals x when we're using linspace. So that's not what we want to use. So when I think of the fact that we want our steps, our change in temperature y, in this case, to decrease as we increase x, which is just some independent variable, we want to use something that looks kind of like a logistic curve like this, right? So let's think of what that might be. So we think of logarithm, so natural log and the exponential of a function. So let's look at that, right? That's not bad, the natural log of x, honestly. Or we could use some sort of exponential growth. But in this case, again, we want it to be decreasing, at least the change in y, which is going to be our temperature. So like this is not exactly what we want. But we want this end, really. Like we want that at the end for y, because these are very, very, very tiny changes in y. So maybe if we flip that, and then flip the exponent sign as well, we do get that. Look at that. Isn't that nice? Okay. And then now we just need to play around with the scale. So we can scale that up to the origin there by subtracting 1, which is good. And this here is the 0, -1. So that's what would allow us to easily do that, because we know where this is going to start. So it'd be good for us to start there at the origin. Now what we need to do is start at some initial temperature that we want to start at. So back in our code here, we started, and we didn't go, like, I didn't mess with the for loop to make it go closer and closer towards the critical point. I just didn't want to mess with that. I figured 500 would be good enough, and it still worked. So we started at 250, so that's absolutely fine. That could be our initial value. Let's change this to x. And let's see. This x will probably, well, we're going to be starting at the origin, so 0 to 10. And again, because we don't want this straight line, we're going to want a lot of points, believe me. So I'm literally going to put in like 500 points here. Okay, but what we need to do with our function here for temperature, what we have so far is excellent, but we need to scale it up the axis, right? And we want to create a limit on that scale. So it needs to have something in front, some scalar multiplier here. And we want this also to have the y-intercept be our initial temperature. So that is going to be, I think it was 250, right? That's what we said. And then our scale is just going to be the difference between the maximum, right, like the highest point of temperature that we're going to get, and then our starting point, which is 250, right? I mean, it's not going to go below that, so I mean, that would be ridiculous. So I don't know what the critical temperature of water is. Let's just go 600, right? Minus the 250. So that should work much better for us. And let's zoom out. There you go. And it looks a little wonky, right? But if we could, honestly, if I can zoom in a little better, it's gonna look the way we want it to look. See? You see that little curve? Like, that is what we want here. This is just different because we are changing things fast, and there's big temperatures. But if you're looking at this, this is what we want to see. And this would be assuming that 600 is our critical point. But let's actually see if this will work. So we have all those points in here, and all we need to do is write our expression for t, which will depend on x. So we'll do x.tc minus our initial value, which will be 250, times 1 minus numpy x exp negative x, right? And then all of this plus 250. And let's see if this works. Does not work, and that may be due to this being too high. Let's drop this to 7. See if that works. It's going to be a little slow because we have so many points, and that does work. It's kind of good news here. Let's see if we get, oh, it does. See, look at that. Look at that. People, that is what we want to see. And I zoomed in properly. So that looks absolutely beautiful. But notice that the temperature change does depend on x. So I just want to make it clear that the reason that this didn't work before is that 10 made our temperature value, you know, the change go too high, and it surpassed the allowable point, which in this case would be the critical point where those things meet. So this is actually excellent. This is exactly what we wanted to see. We have this nice smooth curve now. So I hope this video was edifying for you, and I hope you got to see how we can solve certain problems like that when we are using a for loop to adjust a certain variable. In this case, it was temperature. How we can actually just make that depend on another variable and use a for loop with that. In this case, it was x, so that we can model our step change in temperature. Because in this case, we wanted to take smaller and smaller changes in temperature as we approached that critical point, and that is what allowed us to get our beautiful two-phase envelope. And again, so like on one side we have the specific volumes of the liquid, specific volumes of the gas, and they come to meet right at that critical point. So I hope this was extremely helpful for you. Thank you so much for watching.